Today let us discuss about fundamental theorem of arithmetic. Every positive integer n greater than 1 can be expressed as a product of primes. This representation is unique apart from the order in which the factors occur. For example, if you take the integer 12, it can be expressed as 2 into 2 into 3. Here all the integers 2, 2, 3 here are prime numbers. The theorem says that any integer can be represented as a product of prime numbers. And this representation is unique apart from the order in which the factors occur. That is, we can write 12 as 2 into 2 into 3 or 2 into 3 into 2 or 3 into 2 into 2. The factors may occur in different orders, but the primes involving the product is unique. That is what you meant by the statement of the theorem. So let us prove the theorem. Let n be an integer greater than 1. If n itself is a prime number, there is nothing to prove. Because if we take n as 3 or 5, it is actually equal to a prime number. Here we can consider it as product of primes. So trivially, there is nothing to prove. Otherwise, that is, if n is not a prime number, that is, if n is a composite number, then n has at least one divisor such that that divisor is greater than 1 and less than n. And that divisor d divides the number n. That is, if we take an integer like 6, 6 is not a prime number, so there must be a divisor for 6. Let it be some 2 or 3. Then 2 is strictly greater than 1 and less than 6, and 2 divides 6. So given an integer which is not a prime number, it may have many divisors. And if we consider set of all such divisors which are all greater than 1, we can use well ordering principle and we can choose a prime number p1 which is the smallest of such divisors. Well ordering principle says that any non-empty set of positive integers has a least element. And clearly, if we take all the divisors of an integer, the smallest integer must be a prime number and we can choose it as p1. Then p1 must be a prime. Otherwise, p1 has a divisor q with 1 less than d less than p1 and d divides p1. That is, if we take again 12 here, 6 is a divisor of 12. But here 6 is not the smallest divisor of 12 because 6 is not a prime number. 6 is a divisor of 12 which is a composite number. Therefore, there must be another integer which is a prime which divides 6. So here 2 divides 6. And we know 2 divides 6 and 6 divides 12 implies 2 divides 12. Therefore, if we take a divisor of an integer which is not a prime number, then there must be another integer less than that composite number which is a divisor of given integer. Therefore, if we choose the smallest divisor of any integer, it must be a prime number. If we choose the smallest divisor of the integer, it must be a prime. Otherwise, what happens? That integer p1 has a divisor q which divides p1 and d divides p1 and p1 divides n. Like this, 2 divides 6 and 6 divides 12. Then 2 divides 12. Likewise, d divides p1 and p1 divides n implies d divides n, where 1 is less than d less than n. But this is a contradiction because we already assumed that p1 is the smallest divisor of n. But here d is a divisor of n and d is less than p1. But p1 is the smallest divisor of n. So this doesn't happen. Therefore, we can say that if we choose the smallest divisor of any integer, it must be a prime number. Therefore, if n is the given integer and p1 is the smallest divisor of n, n can be written as p1 into another integer n1. Where p1 is a prime and 1 less than n1 less than n. That is, here n is p1 into the integer n1. Since p1 is greater than 1, n1 must be less than n. If n1 is a prime, then the proof is complete because we get n as a product of two primes p1 and n1 if n1 is a prime. Otherwise, we can repeat the same argument. That is, if n1 is not a prime, then we can express n1 as p2 into n2, where p2 is a prime and n2 is an integer which is less than n1. Now we can write n as p1 into n1, that is p1 into p2 n2, where 1 less than n2 less than n1, and this n1 is less than n, so we can say 1 less than n2 less than n1 less than n. If n2 is a prime, we can complete the proof. That is n equal to p1 into p2 into n2, where n2 also is a prime. Therefore we get n as a product of primes. Otherwise, we repeat the same argument again and again, and we obtain a decreasing sequence n greater than n1, greater than n2, greater than n3, greater than etc., greater than 1. And this sequence cannot continue indefinitely because after a finite number of steps, the sequence terminates with some nk minus 1, which is a prime, and call it as pk. Note that here we have a decreasing sequence. All the integers in the sequence are greater than 1. And the integers goes up to only n. We starts with n, and n1, n2, n3 are all integers less than n which are greater than 1. So in this sequence there can be at most n minus 1 integers. So this sequence terminates as some nk minus 1, which must be a prime number, and we call it as pk. So we can write n as p1 into p2 into p3 into etc. into pk, which is a product of primes. Now we have to establish the uniqueness of this expression. That is, to establish the uniqueness of prime factorization, assume that n can be represented as a product of primes in two ways. Say n equal to p1 into p2 into etc. into pr. Also n equal to q1 into q2 into etc. into qs. And without loss of generality, we may assume that this r is less than or equal to s. Here pi and qj are all primes, and we write the primes in the ascending order, that is p1 less than or equal to p2 less than or equal to etc. less than or equal to pr, and q1 less than or equal to q2 etc. less than or equal to qs. Now we have p1 into p2 into etc. pr equals q1 q2 etc. qs. That is, this one q1 q2 etc. qs equal to p1 into an integer. Here p2 etc. pr can be considered as a single integer. So p1 into an integer gives the product q1 q2 etc. qs. Therefore we can say this p1, which is a divisor of q1 q2 etc. qs. So p1 divides q1 q2 etc. qs. But we have already studied a result that if a prime number divides a product of primes, then this one equals one of the primes in the product. That is, here p1 divides q1 q2 etc. qs implies p1 equal to qk for some k where k lies between 1 and s. So in this product, p1 equals one of the primes in the product q1 q2 etc. qs. So actually in the product q1 q2 etc. qs, here lies some qk, and we assumed that this equal to p1. Therefore this p1 must be greater than q1. Since qk is greater than or equal to q1, we can say that p1 is greater than or equal to q1. That is our first expression. Now again we consider this expression. Here we may consider it as q1 into an integer. q1 q2 etc. qs can be considered as an integer, and we may say q1 into an integer gives the product p1 p2 etc. pr. Therefore q1 is a divisor of this expression. That is, q1 divides p1 p2 etc. pr. As in the previous argument, we may say q1 equal to one of the primes in this product, that is q1 equal to pl for some l here, where L lies between 1 and R. Here also we may say we have the product P1, P2, etc. PR. PL is somewhere here, and we showed that is equal to the prime Q1. Here P1 is here PL is greater than or equal to P1 as per our assumption. So we may say Q1, PL equal to Q1, therefore Q1 is greater than or equal to P1. So this is our second expression, Q1 greater than or equal to P1. So by 1 and 2 we can conclude that P1 equal to Q1. Therefore in our expression N equal to P1, P2 etc. PR equal to Q1, Q2 etc. QS, we showed that P1 equal to Q1. Therefore we may cancel the same factor from both the products and we may write P2, P3 etc. PR equal to Q2, Q3 etc. QS. So if we continue the same process again and again, we may prove that P2 equal to Q2, P3 equal to Q3 etc. And we may cancel the same factors from the products. And if the number R equal to S, all the terms will be cancelled. In that case, we showed that both these products are actually equal. Therefore, since we have the product N equal to P1, P2 etc. PR and again N equal to Q1, Q2 etc. QS. We showed that this P1 equal to Q1, P2 equal to Q2 etc. PR equal to QS since R equal to S. So if R equal to S, both these products are equal. What happens if R is not equal to S? That is, in the product Q1, Q2 etc. QS, there are more primes than in the product P1, P2 etc. PR. What happens then? So we have if R less than S, we already assumed that this R is less than or equal to S. So if R equal to S, our proof is complete. And if R is strictly less than S, what happens? Then the product is like this. P1, P2 etc. PR equal to Q1, Q2 etc. QR, then QR plus 1 etc. QS. So we may cancel the same factors from both the products. P1 equal to Q1, so it cancels. P2 equal to Q2, it cancels, etc. PR equal to QR, it cancels. So what remains? We have in the left side it is 1 equal to QR plus 1, QR plus 2 etc. QS. But it's an absurd statement because these are all primes. QR plus 1, QR plus 2 etc. QS are all primes. Prime should be greater than 1 and product of integers which are greater than 1 cannot be equal to 1. So this statement is an absurd statement. So we may conclude that this never happens. That is, R must be equal to S if N equal to P1, P2 etc. PR and if N equal to Q1, Q2 etc. QS. So we proved that R equal to S and P1 equal to Q1, P2 equal to Q2 etc. PR equal to QR. So this makes the two factorizations of N as identical. Hence our result is complete. That is, we can express N as a product of primes in a unique way. Now we have a corollary. Any positive integer n greater than 1 can be written uniquely in a canonical form n equal to p1 raised to k1, p2 raised to k2, etc. pr raised to kr, where each pi is a prime and ki is a positive integer for 1 less than or equal to I less than or equal to r and p1 less than p2 less than etc. less than pr. In the theorem we have already proved if n is any integer, we can return n as a product of primes, say p1, p2 etc. pl, where each pi is a prime and p1 less than p2 less than etc. less than pl. That is, in this representation, each of these integers p1, p2 etc. pl are primes and these are appearing in an ascending order. That is, p1 is less than p2 less than etc. less than pl. So while arranging primes in this manner, some of the primes may be equal. For example, p1, p2 etc. some ps may be equal, then ps plus 1 etc. pq may be equal, etc. For example, if we express 12 as a product of primes, we have 2 into 2 into 3. That is, first two primes are equal. So we can express this as 2 raised to 2 into 3 raised to 1. That is what generalized here. So in this representation of n as a product of primes, we combine the primes which are equal. Then we can express this as p1 raised to some positive integer k1 into P2 raised to some positive integer K2, etc. PR raised to some positive integer KR. And when we express an integer in this form, it is known as the canonical form of the integer. For example, if you want to express 20 in the canonical form, we have to factorize 20. So we have here 20 by 2 gives 10, again divided by 2 gives 5. So we can express 20 as 2 into 2 into 5. That's equal to 2 square into 5 raised to 1, which is the canonical form of 20. Let us express 360 in its canonical form. So divide 360 by any prime. So 2 divides 360. So we have 360 by 2 gives 180. Again divided by 2 gives 90. Again divided by 2 gives 45. Then 2 doesn't divides 45. So which is the next prime which divides 45? It is 3. When we divide 45 by 3, it gives 15. Then 3 divides 15. So we have 5. So we can express 360 as 2 into 2 into 2 into 3 into 3 into 5. We can combine the like primes and we have 2 raised to 3 into 3 raised to 2 into 5 raised to 1, which is the canonical form of 360.